Alrighty, so let's go ahead. This is gonna be page 102, chapter 24, which is going to be talking about electromagnetic waves. And we have actually talked about waves before, right? So when you have two straight wires connected to an AC terminal, they can generate electromagnetic waves. So let me go ahead and write this down. You have two straight wires connected to the terminals. Of an AC generator. You can create an electromagnetic waves. Now, when you have an electromagnetic wave, let me go ahead and do this down. Let's say, actually, let me go ahead and use black. And then let's say we have an electric wave. Now, the electric wave, we're gonna, electric field, electric field, this electric field wave. Now, the electric field is gonna generate a magnetic field. This magnetic field is gonna be perpendicular to the wave. So I'm gonna try to draw it as best as perpendicular as I can. So perpendicular. Now, the speed of the electromagnetic wave in a vacuum we give it a letter C, which is going to be approximately 3 times 10 to the 8 meters per second. Now, again, we define, actually, make it a new one. We define the speed of a wave as your frequency multiplied by your lambda. And again, lambda, that's your wavelength. And F, that's your frequency. So let's say we have, let's say this is our frequency chart. And your frequency is actually going more frequency this way, less frequency that way. Now, if you actually look at the chart, if I'm not mistaken, between me go ahead and get this. Let's say it's right now between over here. If I'm not mistaken, it's between 10 to the 14th to from the 4 times 10 to the 14 to 7 times 10, 8 times 10 to the 14. That's our frequency range, and that's where you actually go see the different colors of the rainbow spectrum. So you get your red, and then you get your orange, and then your yellow, green, you get your purple, and then your blue, and then you get your violet, which let's go ahead and call that the violet right now. So you remember your spectrum goes in from, which is your rainbow colors, from red to violet. Now, after that, you're gonna have probably up to here, you're gonna have your ultraviolet waves. And then after your ultraviolet, you get your X-rays. And then over your X-rays, that's where you get your gamma rays. And gamma rays are really harmful to you. That's where actually you can, you die as soon as you get exposed to them. Now, under them, so you get the red. Over here, you're gonna have your infrared. And then you get your microwaves. And then your radio waves. Which, the funny part is, or the interesting part, that your FM radio waves actually included in the microwave region, while the outside region where you get the radio waves, that's where you have your AM module in there. Now, and again, because your velocity equals to your frequency multiplied by your lambda, that means for this one, the speed of light is going to equal to the frequency that we have for the spectrum multiplied by your wave length. So let's say we have a question. We take this question, we go ahead and copy and paste. Find the range wavelengths for this visible light. Frequency between 4 times 10 to the 14th and 7.9 times 10 to the 14 hertz. So your frequency for your first one is going to equal 4 times 10 to the 14th hertz. The frequency for the second one is 77.9 times 10 to the 14 hertz. And in both cases, we want to find the wavelength associated with it. Now, in both cases, your C equals F lambda. That means your lambda equals your C divided by your F, which is going to equal to 3 times 10 to the 8 divided by 4 times 10 to the 14th. Well, for this one, you should get 750 nanometers. And for this one, divided by 7.9 times 10 to the 14, so you should get 380 nanometer, and that's exactly what we had. Perfect. Now, you see your speed of light, let me go ahead, I'm not gonna go through the whole math of this for this class, but I'm gonna explain how the speed of light, so this guy named Maxwell. And he did a prediction for the speed of light. Now, if I'm not mistaken, he did it in 1861, if I'm not mistaken. So what he said, and I'm not gonna go through the whole math of this, but your speed of light was gonna equal to 1 over square root of something called epsilon naught mu naught. Now, your epsilon naught, that's called your permittivity. Permittivity. And actually get a different color for this. Your mu naught, that's gonna be called your permeability. Permeability. Now, your the value of the permittivity is, actually, let me get a different, let me go back to red on this. 8.854 times 10 to the negative 12 farads per meter. And your value for your permeability is your 4 pi times 10 negative 7 Newton per amps squared. Now, putting in these together, you should be able to get 2.99 times 10 to the negative 8 meters times 10 to the 8 meters per second, which we actually, you can go as simplified as 3 times 10 to the 8 meters per second. Now, we got this wave over here. Now, the intensity for it, and I'm gonna be going, again, we define the intensity as I, but your book likes it as S. So the intensity for it is how much power over your area. So that's your area, and that's your power. So let's take a little question, shall we? Let's go and take this question about Neil Armstrong. All right, so what we got? All right, so you got, for part A, you got the distance. Neil Armstrong was the first person walking on the moon. The distance between the Earth and the moon is your distance as 3.85 times 10 to the 8th meter. Find the time it took his voice to reach Earth via radio waves, where so you're looking for your time. That means where, again, let me give a reminder that your velocity is your distance over your time. In our case, your c is your distance, which is your speed of light, distance over time. That means your time was your distance divided by speed of light c, which is going to be 3.85 times 10 to the 8 divided by 3 times 10 to the 8 power. So you should get about 1.285 seconds. Part B. Now, someday a person will walk on Mars, which is 5.6 meters from the Earth. So right now your distance changed to 5.6 times 10 to the 10 power. Your distance is 5.6 times 10 to the 10 power meters, which we're looking for time. And again, from both of these, which we already did, your time is your distance over your velocity, which is going to be your c. So it'll be 5.6 times 10 to the 10 divided by 3 times 10 to the 8. So we should get 5, 6 would be 1905, 190 seconds. Okay, let's do another question, shall we? All right, let's go ahead and take this question in. Okay, truck driver is broadcasting at a frequency of 30.697 megahertz, and which means actually so 30.697 times 10 6 hertz. And what we're looking, so we said to use this one as 2.9979 for the speed of light times 10 to the 8th power meters per second, and we are looking for your wave length. And again, your v equals f lambda, so your c actually equals f lambda because that's your velocity, which means that your lambda is going to equal to your c over f, which is going to be your 2.99 times 10 to the 8th divided by the 30.697 times 10 to the 6th. And you should get 9.76 meters for your wave length. Let's do another question. Go ahead and do this question over here. Okay, you got two astronauts that are 2.9 meters apart. So your distance in this matter is 2.9 meters. Once the spaceship, the conversation started to the Earth, the time it takes to the sun will travel, so your velocity this time is 343 meters per second. How far away from the Earth is the spaceship? So I'm going to call this the spaceship. So out of these two, that means your time is going to equal to your distance over your velocity, which equals your 2.9 divided by 343. So you should get 8.5 times 10 to the negative 3 seconds. That means your distance of the spaceship, which is going to equal to speed of light multiplied by, and again, your c equals distance over time, spaceship. That means your distance for the spaceship is going to equal to c multiplied by your time, which is going to be 3 times 10 to the 8th multiplied by 8.5 times 10 to the negative 3. So we should get 3.54 times 10 to the 6 meters. All right, let's do a question about intensity, shall we? So let's say laser emits a narrow beam of light. The radius of the beam is 4.7 millimeter, and the power is 3.5 milliwatts. What is the intensity of the beam? So your power in this case was 3.5 milliwatts. Which actually, let me just go ahead and write it down: 3.5 times 10 to the negative 3 watts. And your radius is 4.7 millimeters, which is 4.7 times 10 to the negative 3 meters. And you're looking for your intensity. Now your intensity, again, your book uses S, so I'm gonna go with your book, is your P over A. But we have the P, we don't have the area. So your area of that is going to be pi r squared for that light, pi r squared. So let me go ahead and write this down. So this one's going to equal to 3.5 times 10 to the negative 3 divided by pi multiplied by r squared, which is your 4.7 times 10 to the negative 3 squared. So what I got is 50 watts per meter squared. All right, let's do one last example. The maximum strength of a magnetic field in an electromagnetic wave is 4.8 times 10 to the negative 6 Teslas, or the maximum strength of the electric field of the wave. So for this one, your magnetic field was 4.8 times 10 negative 6 Teslas. And you're looking for your electric field. And your electric field, actually, I need to actually probably write this down over here. Let me go ahead and write this down. We need to define this. So your electric field is going to equal to your speed of light multiplied by your magnetic field. So your electric field is going to equal to the speed of light multiplied by your magnetic field, which is going to equal to your 3 times 10 to the 8th multiplied by 4.8 times 10 to the negative 6. So you should get 1,400 newtons per Coulomb. And that should conclude chapter 24 for Physics 102. If you have any questions, please email me at abunaem@uah.edu, or you can text me or call me at 256-348-1480. Thank you.